break this up into a c squared times c squared, so I'll get rid of that one, and then I'll distribute here. So this gets to be a1 squared minus 1 times v squared a1 squared plus c squared. So I have a1 to the fourth v squared equals, and FOIL, everyone's favorite algebra exercise. We get v squared a1 to the fourth, wow, that's convenient, times, or plus, a1 squared c squared minus v squared a1 squared minus c squared. Oh, we are so close. Don't forget, I'm trying to solve for a1. And so I've gotten rid of all my b's, so I have an equation with just a single unknown. So I'm going to bring c over to the other side. And I get c squared equals a1 squared times c squared minus v squared. And that's not how we'll work it. So we'll just do, let's just divide by c squared. So I get 1 equals a1 squared, 1 minus v squared over c squared. a1 squared equals 1 divided by 1 minus v squared over c squared. And therefore a1 equals plus or minus the square root of 1 over 1 minus v squared over c squared, which in essence is plus or minus gamma. We had it down that x prime is equal to a1 x minus vt. So if I have, looking at this position right here, I know that x is bigger than vt. X is bigger than vt. I see some people still looking over there, so why don't I pause to give people a chance to catch up. So we have, mathematically, we have two solutions over there. However, only one of them really makes sense. So back to this scenario here, we have the rocket going by at some speed v. I know x, this position right here, is bigger than vt in my scenario. So this is a positive number, this is a positive number, assuming positive to the right. So a1 has to be positive. It doesn't make sense that x prime would be a negative number in this scenario. And so therefore, we have x prime is equal to gamma x minus vt. And we have the first of the two major Lorentz transformations. I'm going to hand wave my through the next bit. I don't think there's anything gained by going into the nitty-gritty detail, which might prompt you to wonder, was there anything to gain in this? I still think yes. But now that we have a value for a1, we know that this is gamma. We can solve for b1. b1 equals negative v over c squared times gamma. It's a very simple process. Once you plug in our value for A1, you put gamma back in terms of V and C. You do the expansion, eventually you do a square root, and you get a plus or minus solution, and then through logic, you identify the negative as the correct solution. And we can do something similar here for B2, and we end up with B2 equals gamma. Or as my college professors used to say, I'll leave the ... left for your other enjoyment. So what we are now down to is we have a relationship between x prime and x. We have a relationship between t prime and t. T prime is equal to b1x, so negative v over c squared gamma x, plus b2t, which is gamma t. We can factor gamma out, put it in a slightly different order, the more traditional order. T prime is equal to gamma times t minus v over c squared x. There are two other Lorentz transformation equations that hopefully will become, when I write them down, you'll go, okay, sure. Because I talked about S prime moving in the x direction, what about the y and z direction? Well, I don't have anything moving in those directions. And so, if I bring in, make it a three-dimensional problem, but this is still moving in the x direction, then we have y prime equals y and z prime equals z. Not earth-shattering, but it does come in handy in a bit. I probably should write those equations neatly because we are about to use them. So x prime equals x, gamma x minus dt. T prime equals gamma t minus v over c squared x. Oh, and then y prime equals y, z prime equals z. Now we have a relationship between them. We can revisit the variation of the car and garage problem. All right. You writing down this part over there, or are you good? Can I erase this? Any objections? Well, it helps with the B. This is I have a 16-foot pole. That's what that's supposed to represent. Sorry, 16-meter pole. We're doing metric. And not to scale. Its proper length is 10 meters. So the pole that's proper length is 16 meters and a barn whose proper length is 10 meters. LP barn. There we go. Here's the notation I want, LP pole. And I have a person running. The two reference frames here, my X frame will be the barn, and this is my origin right here. This is where X equals 0. And from the pole's point of view, this is my X prime frame, and its origin is set at the left end of the pole. The velocity of the pole with respect to the barn is 0.866 times the speed of light. It's a realistic problem.
Super.
So if the speed of the pole is 0.866 times the speed of light, what is gamma? So one of you would be kind enough. And for those who have forgotten, gamma is 1 over the square root of 1 minus b squared over c squared.
Got 1.998. Is that correct? I'm not sure.
All right, we're just going to make it 2. Feel free in your own notes to pick it up farther if you want. All right, so what's going to happen here is the pole's going to come into the barn. As soon as the left end of the pole gets inside the barn, the left and right doors of the barn will close immediately. It's as realistic to close them as instantly as it is for us to get a pole and a person up at gamma is equal to 2. So I have 3 events that are going to happen here. Event 1. Left door closes. Event 2. Right door closes. Event 3. Right end of pole. Crashes into right door. So the first thing we're going to do is we're going to look at it from the barn's point of view, figure out when these events happen, then we'll do it from the pole's point of view. And we will use the Lorentz transformations. All right. Now we need to start the clock at some point. So I'm just going to make the claim that the left door closes, that's when we start the timer. So this is going to happen, the left door closes at the position of 0 meters. So this is my x and t values. 0 meters, because that's where I define my coordinate system, and 0 seconds. Actually, for convenience, I'm going to make this microseconds, or do I want nano? Probably nanoseconds makes more sense. The right door closes at the same time as the left door closes from the barn's point of view, so that's 0 nanoseconds. And let me re-emphasize, this is barn frame. And the right door closes in the barn reference at 10 meters. So to figure out the crashing of the right door, well, that happens at 10 meters, but we need to figure out the time. At what time does the pole hit this? So let's figure out how big is the pole from the barn's point of view. Well, I know that the proper length is equal to gamma times the other length. And so the relativistic length is going to be the proper length divided by gamma, which is 16 meters divided by 2, or 8 meters. In other words, the pole is going to look like it's 8 meters long. That's badly worded. From the barn's point of view, the pole is 8 meters long. So when the left door closes, the tip of the pole is here. Basically, that's the pole from the barn's point of view with 2 meters to spare. So the question is, how long does it take for that pole to go those last 2 meters? Well, it's just simple chapter 2 kind of stuff. I know that distance is equal to speed times time. And so time equals distance over speed. And the distance is 2 meters. And the speed is 0.866 times the speed of light, which is roughly 3 times 10 to the 8th per second. I would have put in the real value, but I rounded the gamma off to 2, so I figured, yeah, let's stick with 3 times 10 to the 8th.
7.698 times 10 to the negative 9.
Units?
Second.
Yep. So the right side of the pole hits the right side of the barn at 7.698 nanoseconds. And so what we need to do is look at this from the pole's point of view. Because from the pole's point of view, the left end of the pole is not moving, and that barn is coming straight at it with the gamma of 2. Matter of fact, from the pole's point of view, how big is the barn? Yes. I figure people were toggling between 5 and 20 there. It is 5.
I was like, from that frame, would it seem smaller or bigger?
Yeah, the thing that's traveling fast relative to you, it's going to be smaller.
Okay.
All right, so what I need to do is figure out what exactly is happening in that frame, and so we will use our Lorentz transformations and figure it out. So the first of it, x prime is equal to gamma x minus vt. And so the first event we have happens x prime is equal to 2 times 0 minus v times 0. I think I got this one. 0 meters. Because the left end of the pole is our reference frame there, and the barn door, the left end closes as soon as that clears it, so they're in the same spot. T prime for event 1, this is event 1. T prime is going to be gamma t minus v over c squared x, which is 2 times 0 minus v over c squared times 0 nanoseconds. In other words, we've synchronized the clocks there. So and we will go for that usual stunning visual effect. So this is pole frame. This happens at 0 meters, 0 nanoseconds. So the barn and the pole have at least one agreement. They both agree that at that moment in time, they both start the stopwatch or the atomic clock, and they both define the reference, or the reference frames are in sync at that moment. Event 2. Plugging into that equation again, x prime is equal to 2 times 10 minus v times 0. And t prime is equal to 2 times 0 minus, we're not dealing with 0 anymore here, so v is 0.866 c over c squared times 10.
I got 5.77 times 10 to the negative 8 seconds.